Hi, everyone. Thanks for coming. My name is David Bakai, and it's my great pleasure to introduce Emmanuel Farhi to give the final plenary talk of this year's SED. Given the breadth of Emmanuel's contributions to different parts of economics, I think it's safe to say that he's really not a man in need of an introduction. Emmanuel's made important contributions to many areas of economics, including public finance, international macro, monetary and fiscal policy, macroprudential policy, decision theory, behavioral economics, bounded rationality, aggregate productivity, asset pricing, sovereign debt, global imbalances, exchange rates, market power and misallocation, international trade, just to name a few of the topics that he's worked on. But for me, the depth of his work is actually much more impressive than the breadth of it. I think Emmanuel's really not satisfied until he gets to the bottom of the issue that he's studying. And I'm very grateful to have had the privilege of seeing him dive deep on some of these issues, first as his student and then as his co-author. So without further ado, please welcome Emmanuel. Thank you.
Thank you, David, and thank you, everybody, for sticking around on a Saturday night in St. Louis. So I'm going to be talking about macro as explicitly aggregated micro. One of the fundamental, this doesn't work actually. Oh, there you go. The magic touch. Okay, this is going really smoothly. So, one of the fundamental problems of economics, and arguably the fundamental problem of macroeconomics, is the aggregation problem. That is the problem about reasoning about economic aggregates. And economists have been wrestling with this question for hundreds of years. In fact, perhaps the first written piece of technical economics, François Quesnay's Tableau économique, was precisely about this problem. The Tableau économique in turn gave rise to general equilibrium theory, to the welfare theorems, and then to the Valrasian and Paretian programs of constructing models of aggregate behavior from the grounds up. Now, this grand vision was derailed in the 70s through a series of negative theoretical results. Results which showed that restriction placed on micro behavior, for example, that demand curves are downward sloping, or that preferences do not violate transitivity, or that there are decreasing returns, actually place no restrictions on the behavior of economic aggregates. So these anything goes type results discouraged the aggregation project. They showed in a variety of contexts that without adding more structure, or without bringing in more data, to discipline the theory, there just wasn't much that you could say in general. Now, in recent times, the study of heterogeneity has made a huge comeback. So there's been an explosion of research on models with heterogeneous agents and heterogeneous firms, building on the pioneering work that was done in the 80s and in the 90s. So we now have access to far more micro-level data than ever before. And the scale, scope, and availability of this data is increasing by the day. For example, there are now a handful of countries that have made their firm-to-firm value-added transaction data available to researchers. That means that allows us to see the input-output network of firm-to-firm transaction at annual and sometimes higher frequencies. Now, obviously, this means that we no longer need to use pure reason to predict the behavior of economic aggregates. But in order to take advantage of this deluge of data, we need flexible theories. We need theories that can consume as much information as we have and that help us aggregate up this information to understand the behavior of aggregate variables. And so this brings me to the topic of today's presentation. I want to talk about the unifying project of building macroeconomics as explicitly aggregated microeconomics. When you think about it, you realize that there are two sorts of heterogeneity that you need to confront. A distribution of heterogeneous agents consuming different goods and supplying different factors, and an input-output network of heterogeneous producers producing different goods using different factors and different intermediate inputs. The objective is to develop a general approach to the theory and measurement of propagation and aggregation with HA, heterogeneous agents, and IO, input-output networks of heterogeneous producers. Now, crucially, the theory and the measurement need to be consistent. And that's usually understood to mean theory-consistent measurement. But given the state of today's practice, I think that it's equally important to insist on measurement-consistent theory. So this project defines the research agenda that David and I have undertaken. Now, obviously, we're not the only ones to be thinking about these questions, but I didn't want this talk to be a survey. So instead, what I'm going to try to do is to give you a general sense of the perspectives and then the methods that we've been developing. I'm also going to try to give you a number of very concrete quantitative and empirical applications that demonstrate their value. And finally, I'm also going to talk about some of the problems and limitations of some existing popular alternatives. So this talk is going to be based on a series of papers that I have with David. They are listed here. Let me go through them very quickly. The first one is on inefficient economies. The second one is on nonlinearities in efficient economies. The third one focuses specifically on economies with heterogeneous agents. The fourth one is about intermediate level aggregation. That means that you're studying not the whole economy, but aggregates that are composed of a group of agents, so an industry or a group of households or something like this. Then we have one on open economies and trade, and we have a paper on the microeconomic foundations of aggregate production function that tries to revisit some of the debates related to the Cambridge Capital controversy. We have ongoing work that I'm not going to be talking about today on increasing returns, on entry and exit, on dynamics, on industry structure, on growth, etc. So it's really a research agenda. Let me start by reminding you of two very powerful first-order aggregation theorems for efficient economies. The first one is due to Solow, and it applies to economies with an aggregate production function. And it says that you can recover the change in aggregate TFP by netting out input growth from output growth. And the way you should weight the growth of the different inputs is according to their factor income shares. The second aggregation theorem is due to Holton, and it applies to disaggregated economies with HA and IO. It says that you can decompose the change in aggregate TFP in the sales-weighted sum of the changes in the microeconomic productivities. Now, the sales shares are also called the Domar weights, and Holton's theorem is a structural foundation for Domar aggregation. Importantly, it is not a definition. You cannot start from the postulate that the aggregate variable is the sales-weighted sum of the disaggregated variable. You need to derive this from first principle as an aggregation theorem, and this is what Holton's theorem does. So these two theorems are absolutely central for everything that we do in macro, from measurement, for example, growth of counting, to predictions, counterfactuals. So for example, if you want to know the answer to the question, how much would aggregate TFP increase if there was a 5% increase in the productivity of Walmart? Well, that's going to be given by the sales share of Walmart. Holton's theorem is also a very powerful irrelevance result. It tells you that if you know the sales share distribution, you do not need to concern yourself with the disaggregated details of the economy. So the input-output network, the number of factors, the returns to scale, the elasticities of substitution, the wealth distribution, the marginal propensities to consume, all these concepts are going to matter only through the distribution of sales shares. It also says that the initial level of aggregation is irrelevant. So you can apply Holton's theorem equally at the product level, at the firm level, or at the industry level. Powerful as it is, Holton's theorems also have very significant limitations. It fails in inefficient economies. It fails at higher order of approximations relevant for nonlinearities in efficient economies. When that happens, the disaggregated details of the economy and the initial level of aggregation is going to matter. And to handle those, we're going to need new theories to think about inefficient aggregation and to think about nonlinear aggregation. So I'm going to be spending a considerable amount of time talking about these two things. But before doing so, I want to spend some time unpacking the logic behind Holtons' theorem. So one question that you guys might have is why sales share and why not value-added shares, for example? So this is a very simple example to convey the point. This example is a vertical economy. Producers are arranged on a vertical chain. The first producer produces from labor, linearly, and then the other producers are just transforming the good that's immediately upstream from them linearly, and eventually it's sold to the household. And these different producers experience different productivity shocks, AK. So note that there's absolutely no value added in this economy except for producer N. The other producer do not use any value added. Their value added share is equal to 0, but their sales shares is not equal to 0. It's equal to 1. Now think about the level of aggregate output in this economy. It's just going to be proportional to the products of the different productivities. So the elasticity of aggregate output to one of the productivity shock is going to be equal to 1, the sales share, and not equal to 0, the value added share. Okay. Now, it's obviously a very simple economy, and it's simple in a specific sense, that there's no substitution and there's no reallocation. There's one allocation. Okay? So how do we think about more complex economies and how Holton is going to apply to more complex economies? So to think about those, the critical thing is going to be to handle, to find a tractable way to handle reallocation effects. And we're going to do it with the following formalism. So an allocation, any feasible allocation, is going to be entirely described by the productivities of the different microeconomic producers and by the allocation matrix, chi. What is chi ij? It is the fraction of the output of j that is used by I. So it is a physical allocation matrix. It's very different from an input-output matrix. It makes no reference to prices or to expenditure shares. It's just telling you how the resources are allocated in the economy. So if you know the productivities and if you know how the resources are allocated, you know the allocation. And in particular, you know exactly what's going to be the aggregate level of output through this aggregate output function. Now, in equilibrium, there's going to be a particular allocation of resources, a particular allocation matrix. Okay? And so we can expand the change in the equilibrium level of output into its different components. The changes in the equilibrium level of output that are due to the changes in productivities holding the allocation of resources constant, and the change in the equilibrium level of output that are due to the change in the allocation of resources holding the productivities constant. Importantly, the changes in the allocation of resources are occurring because of the productivity shocks, but we are holding the productivity shocks in the first argument of this function. So the first term we're going to interpret as the pure technology effect. What is the pure effect of technology where you do not allow any reallocation? And the second term we're going to call the reallocation effect. What are the potential effects on GDP when you reallocate resources holding technology constant? So I just rewrote this decomposition, and Holtons' theorem is really a collection of two results. The first result tells you that the pure technology effect is given by the sales-weighted sum of the microeconomic productivity shocks. Okay? So the Domar weights are the central objects to think about the pure technology effect, as in the vertical economy that I showed you. The second result behind Holtons' theorem is that there are zero reallocation effects. Now, obviously, it doesn't mean that there are no reallocations in this economy. Resources are reallocated, but these reallocations have no effect in and of themselves on the level of aggregate output. Okay? So Holtons' theorem is basically an envelope theorem. This is what this is saying. Now, let me move on to sort of more complicated economies that are not covered by Solo's theorem and Holtons' theorem. So we're going to start thinking about inefficient aggregation. We do not have aggregation theorems for inefficient economies, and I'm going to try to provide you theorems to do that. So I need to introduce some notation. How am I going to capture the distortions? I'm going to saturate the model with wedges. That means that there can be a wedge in any economic transaction in the model, a wedge that is specific to this particular transaction. For example, when producer I buys from producer J, there can be a wedge tau ij. Now, I'm going to use a representation theorem, which is going to allow me to represent all these wedges as markups by relabeling the network. The way it's going to work is extremely simple. Imagine that you have a wedge tau ij between I and j. What I can do is introduce a specialized fictitious producer between I and j, which is going to transform j into an input for I. And then this producer is going to charge a markup equal to the tau ij, the initial wedge that we're trying to represent. So this new economy, this relabeled economy, is literally isomorphic to the original economy. So it's just a representation theorem, okay? And it's going to turn out to be convenient. So looking forward, I'm going to be relying on this representation theorem. I'm going to be talking a lot about markups, but in the back of your mind, you should understand that you can translate all these results to results about wedges in general, okay? So these wedges could apply to financial frictions. These wedges could apply to distortions in input markets, all sorts of stuff. Now, given that we have the productivities and the markups, we know what the equilibrium allocation matrix is going to be. Okay, so the primitives in this model are going to be the productivities and the distortions. And if we know the productivities and the distortions, which might be endogenous, it's not a problem, we know the allocation matrix. Okay? And then we can represent the equilibrium level of output as a function of productivities and these wedges through this output function. Now, we can perform our decomposition. And we're going to see that the two legs of Holtons' theorem are going to break. The pure technology effects are no longer going to be given by the Domar weights. And there are going to be non-zero reallocation effects. Okay? So before showing you a result that's going to replace Holtons' theorem, I'm going to show you why these two legs can break in two simple examples. So first, I'm going to go back to the vertical economy. So what I'm changing compared to the previous vertical economy that I showed you is that now there can be markups or wedges. So the producers, on top of having a productivity shock AK, are charging a markup mu k. Okay? And we're going to be interested in a productivity shock to producer k. Now, you can see that in this economy, the markups are not going to do anything. Okay? There's one allocation. That's true with markups. That's true without markups. Okay? So that means that when I look at the elasticity of aggregate output to the productivity shock of producer K, it's still given by 1. Now, the Domar weight, the sales share of producer K, is no longer going to be equal to 1. Why? Because you have markups. You have double marginalization downstream from producer K. And this is going to reduce the sales share of producer K. Instead, 1 is going to be equal to a different Domar weight that we're going to call the cost-based Domar weight. And I'll give you a general theory of this cost-based Domar weight in a few minutes. Okay? So that's that part. And then trivially in this economy, there are no reallocation effects because there's no reallocation in the first place. So that tells you why the first leg of Holtons' theorem break. Okay? Why the pure technology effect is no longer given by the Domar weights. It's now going to be given by the cost-based Domar weights. To understand why the second leg of Holtons' theorem breaks, we're going to need a slightly more complicated example, but still relatively simple. So we're calling this a horizontal economy. It's horizontal in the sense that she likes it. So a horizontal economy, you have one factor of production, it's labor, there's no intermediate inputs, and you have a bunch of producers that are producing linearly from labor. They have different productivity shocks and are charging different markups. And then the household is going to buy these different goods, and he's going to value these goods through a CES aggregator with an elasticity of substitution theta 0. Okay? So what is the allocation matrix in this economy? It's how labor is allocated. Okay? So the first component is just the fraction of the overall stock of labor that goes to producer 1, etc., for all the producers. Now, we're going to, again, look at the productivity shock to producer K. So we can, again, do our decomposition. In this economy, the cost-based OMR weights are going to coincide with the revenue-based OMR weights because there are no downstream markups for any producers. So the pure technology effects are going to be given by the DOMR weights. What's going to break is the absence of reallocation effects. There are going to be reallocation effects. Okay? And the magic is that these reallocation effects are going to be given by the reduction in the labor share. So everything you need to know, okay, to know if allocative efficiency improved as a result of this shock is whether the labor share went up or whether the labor share went down, and by how much. Now, what's the intuition for this? Imagine that goods are substitutes, theta 0 is greater than 1, and imagine that producer K is charging a higher markup than the average markup. Now, there's a positive productivity shock to K. The pure technology effect is what's happening where we're not allowing labor to be reallocated. So with the given amount of labor that it had, producer K is now producing more. But of course, because of this productivity shock, the price of K is dropping. The consumer is going to reallocate expenditure towards producer K. Labor is going to be reallocated towards producer K. And that means that the labor share is going to go down. Why is the labor share going to go down? Because producer K has a higher markup than the average markup. Why is that a good thing? Well, producer K was too small to begin with precisely because it had a higher markup than the average markup. It was too small to begin with from a social perspective. So we're moving resources to a part of the economy that was too small to begin with from a social perspective. We're improving allocative efficiency. We're magnifying the effects of the technology shock on aggregate output. Notice that it makes no reference to the productivity of producer K. So this is not about reallocating resources to a more productive producers. It makes no sense to compare the productivities of producers across different producers that are not producing the same good. It's really a second-best intuition. Was the place that we are allocating towards more distorted than the average? And are we improving allocative efficiency or not? Okay. Now, to generalize these ideas, I'm going to need some HAIO notation. So there are going to be two classes of objects, the revenue-based ones without tildes and the cost-based ones with tildes. So let's start with the revenue-based ones, which are the conventional input-output object. The first one is omega ij, the input-output matrix. It records the expenditure of I on j as a fraction of the revenues of I. So it's a notion of direct exposure. Then we have the Leontief inverse matrix. It's defined as I minus omega minus 1, which you can expand as a Taylor series as I plus omega squared, etc. So the different powers of this expansion correspond to the direct and indirect exposures through chains of different length from one producer to another producer. I can be exposed to J directly or indirectly through K or indirectly through K and L, etc. Okay? And so the Leontief inverse matrix is going to record these direct and indirect exposures. With the Leontief inverse matrix and with the vector of final expenditure shares, we can recover the sales shares or the DOMR weights. And we're going to single out some particular DOMR weights, some particular sales shares. It's the sales shares for factors, the DOMR weights for factors, and we're going to denote them with a capital lambda. So that's it for the revenue-based objects. Let me now turn to the cost-based object. I'm going to start with a cost-based input-output matrix, omega tilde ij. The difference with omega ij is that it records the expenditure on I, from I on j as a fraction of the cost of I, not as a fraction of the revenue of I. And because I charges a markup, the cost of I are going to be smaller than the revenues of I. And so omega tilde ij is going to be lower than omega ij. So that's a notion of direct exposure in cost. You can compute a corresponding cost-based Leontief inverse matrix, cost-based DOMR weights, and cost-based DOMR weights for factors. Now, I can state the aggregation theorem that's going to replace Holtons' theorem for inefficient economies. And this theorem is as follows. The pure technology effect are going to be given by the cost-based DOMR weights, not the revenue-based DOMR weights. And the reallocation effects, the changes in allocative efficiency, are going to be given by the changes in the wedges and by the changes in the factor shares. So let me talk about each of these two terms. Forget the wedges for a second. Imagine that we're only talking about productivity shocks and that the wedges are staying constant. Then you see that this object is going to be a weighted average of the changes in the factor shares. Why is it a weighted average? Because the cost-based factor shares, the lambda tildes, are always going to sum up to 1. By contrast, the revenue-based factor shares are not necessarily going to sum up to 1. There are markups, there are distortions. So you can interpret this thing as a weighted average of the reduction in the factor shares. That's the object that generalizes the reduction in labor share that I showed you in the horizontal economy. Now, what's happening when you have changes in markups or wedges? When you have changes in markups or wedges, they're going to trigger directly an increase in prices, which is going to reduce the labor shares. And that has nothing to do with reallocation effects towards more or less distorted parts of the economy. So you want to net it out from the changes in the factor shares to isolate the changes in the factor shares that are coming from these reallocation effects. Okay? So you see that the disaggregated details of the economy and the initial level of aggregation are going to matter. Why? Because you cannot compute the cost-based factor shares, or you cannot compute the cost-based Domar weights based on simple observables like sales shares. You need the whole input-output matrix and the distribution of wedges in the input-output matrix to compute these objects. Now, you also see that this theorem is formulated in terms of changes in endogenous objects. Okay? The changes in the factor shares are endogenous. And this theorem is not giving you a structural formula. It's not helping you how the factor shares are going to change as a function of microeconomic primitives. So as such, in isolation, it's directly useful only to do growth accounting and measurement when you see the economy evolve through the shock and you observe the changes in the factor shares that are caused by the shocks. It's not directly useful to do counterfactuals. To do counterfactuals, we're going to need to combine this theorem with propagation equations that are going to tell you how shocks are going to propagate in the economy, how sales shares and factor shares are going to change. And this is what these propagation equations, which is the second leg of these theorems, are doing. So I'm only showing you the propagation equation for sales shares. You can derive similar propagation equations and actually much easier for prices and for quantities. Okay? So the ones that are hard, the key ones, are really the propagation equation for sales shares. Now, I'm showing them to you in a slightly simplified version of the full general model, where you have a nested CS economy, you have only one factor, and you have a representative agent. But we can generalize this formula by relaxing all of these conditions. But it's already a fairly general economy. It's any kind of nested CS economy that you can imagine, with any pattern of nesting and any distribution of elasticity. So what you see is that these propagation equations are given by a sum over producers of these terms. Lambda j, so that's how big the producer is. Theta j minus 1, that's telling you how big is the elasticity of substitution of this producer. And you see that Cobb-Douglas is going to be a very important benchmark there, where the sales shares are not going to move. And then you see these input-output covariances that are basically sufficient statistics of the input-output network. So I don't have time to go into the details of this object, but you should know that basically this covariance is recording the following. You look at producer J and say there's a shock to the productivity of producer K. Now, that means that the different inputs that J is buying are going to see their prices changing. Okay? And the inputs that are more exposed directly and indirectly to the shock to K, their price is going to decrease by more. If the goods are substitutes for producer J, that means that producer J is going to substitute in expenditures towards these branches, towards these input branches. And then the question is whether these input branches are also more exposed to producer I, because we're trying to trace how the expenditures on producer I is changing when there's a shock to K. You can extend these equations in many ways. And one of the things I want to emphasize is you can apply these equations to models with endogenous wedges. I didn't show you a theory of the determination of the wedges. I'm treating the wedges as parameters that I can shock. But you can impose a superstructure on this model, which allows you to determine these wedges. For example, it could be a model of oligopoly, okay, where you would derive the endogenous markups from the market structure. And then you could feed the changes in markups through these equations to figure out what their impact is going to be on aggregate output, on sales shares, etc. Now, let me explain how you would use this theorem to do growth accounting. So the goal is to do growth accounting with distortions. And the thing you have to realize is that it's very difficult to come up with a very satisfying notion of aggregate TFP in these economies. Okay? So we're going to define a new notion of aggregate TFP. And that's the way we think aggregate TFP should be defined, through what we're calling a distorted Solow residual. So you see that we're recovering the change in aggregate TFP by netting out input growth from output growth, just like in Solow's theorem. But we're weighting the growth of the different inputs, of the different factors, using the cost-based factor shares, not the revenue-based factor shares. Okay? And to construct these cost-based factor shares, again, you need the whole input-output matrix and the whole distribution of wedges. Why do we think it's the right object to capture aggregate TFP? Well, why are we netting out input growth from output growth? The idea is that output goes up also because factor goes up. Okay? And factors go up has nothing to do with productivity. So we want to net out the effect of the growth in factors on aggregate output to be left with something that looks like productivity. So we're well equipped to do this because this large term over here is going to precisely record the pure technology effect of increasing the factors. Okay? So this is the way you should define aggregate TFP in these economies through this new distorted Solow residual. And on top of that, you can decompose this distorted Solow residual, this measure of aggregate TFP, into pure changes in technology and changes in allocative efficiency. Okay? And so you can perform this decomposition without imposing any parametric assumption on production functions. So some of you might recognize some features that look a bit like the results that were derived by Bob Hall in a series of papers in the late 80s. But the results that Bob Hall derived applied only to economies with an aggregate production function. These are economies with no misallocation. They do not apply to disaggregated economies with misallocation. Okay? So this theorem generalizes the insights that Bob derived to disaggregated economies with distortions. Okay? It also gives you a different interpretation of some of the Solow residual failure of irrelevance result that he derived. So he observed that when he computed the change in aggregate TFP in the right way, okay, the change in aggregate TFP was correlated with things that seemingly had nothing to do with aggregate TFP. For example, changes in government expenditures or things of that sort. And then he went on to give a series of explanations as to why that might happen. But the way he applied it is he applied it to different industries. So if you think that industries are composed of different firms, and that there's misallocation within the industries because there are different wedges within the industries, then it's perfectly reasonable to assume that the instrument that he was looking at would trigger reallocations within the industry and would result in changes in measured industry TFP. Now, let me say a few words about some alternative decompositions. And there are two categories of alternative decompositions, and some of these decompositions are very popular. And I'm going to criticize them. So the first ones are statistical decompositions. And the second ones are economic decompositions. These are some statistical decompositions. So I listed a few popular ones. Perhaps the most popular among those are Bailey et al. And Oli Pekas. So what do they do? Okay. What they do is they do not decompose the change in aggregate TFP. They build an ad hoc aggregate TFP index, okay? Then they decompose the change in this ad hoc TFP index, and they try to interpret this decomposition as pure changes in technology and reallocation effects. So for example, this is what Bailey et al. Do. They tell you our productivity index is going to be the sales weighted average of the levels of the individual productivities. And we're going to decompose the change in this sum. And this is the decomposition that they propose. And they're going to call this effect the technology effect, the pure technology effect. And they're going to call this effect the reallocation effect. Okay. The criticism will come in a few minutes, but you can already see that one of the things that it is not a decomposition of aggregate TFP. It is a decomposition of an ad hoc TFP index. This is not the change in aggregate TFP. Let's think now about economic decomposition. So the most popular ones are Jorgensen et al., Basu-Fernald, and Petrin-Levinson. So these are decompositions of aggregate TFP. Okay? They're not the same thing as the statistical ones. But I would argue that they are ad hoc decompositions of the changes in aggregate TFP. So what they do is they start with an equilibrium, they perturb this equilibrium, and then they group terms into groupings that look like changes in technology and that look like changes in allocative efficiency or reallocation effects. So I'm going to call that grouping of terms. It's very different from what we do, which is to base this decomposition on a general equilibrium counterfactual. Okay? So for example, this is what Jorgensen et al. Do. They say we're going to call by fiat, pure technology, the sales-weighted sum of the changes in microeconomic productivities, and the residual we're going to call reallocation. Okay? Note that this pure technology effect is different from ours because it uses the Domar weights and not the cost-based Domar weights. That means that the reallocation effects are also going to be different. Now, what's the problem with these decompositions? They can be very misleading. And in particular, one way to see that, okay, and I'm not saying it's the only problem that they have, but you really see that they run into problems in these examples. They're going to detect reallocation effects even when they really unambiguously shouldn't. For example, they can detect reallocation effects in efficient economies, and they can detect reallocation effects in economies when there's no reallocation. So here's an example, a revealing example of how they can go wrong. It's not realistic, okay? It's an example that's a proof that there's a conceptual problem in those decompositions. It's an example of acyclic economies. What is an acyclic economy? It's an economy where there's a unique path from a factor to the households. There are no diamonds, there are no cycles. That means that there's a unique allocation. There's no ambiguity how to allocate resources anywhere in this economy. By construction, this unique allocation is efficient. Okay? So there are no reallocation effects by construction and no changes in allocative efficiency. Yet all these other decompositions, the statistical ones and the economic ones that I mentioned, will detect changes in allocative efficiency in this economy. And ours will not because it is based on a general equilibrium counterfactual. Let me show you now an application of these growth accounting decompositions. And this is going to be an application to markups in the US. So I'm going to make a number of heroic assumptions and imputation because I don't have the perfect data to implement my theories. Okay, but I'm going to do the best job I can. So I'm going to suppose that markups are the only distortions. I'm going to use the annual input-output tables from the BEA. I'm going to be operating at the firm level with CompuStat. So I'm going to assign the CompuStat firm to different industries. And I'm going to use firm-level markups from 3 different approaches. The first one is a very simple one. It's called the user cost approach. The second one is the production function approach that Jan talked about yesterday. And the third one is an approach based on accounting profits. This is what Harburger used in his famous article. And then we are going to aggregate up from the firm level and perform the decomposition. So there's one thing that's very important about these markup series, and that's common to all 3 methods of constructing the markups. The quantity effects are a bit different, but this qualitative feature is always there. So here I'm showing you the result with a user cost approach to building markups. So not the one that Jan showed you, a simpler one. Okay? But the same goes with their approach. So this is a decomposition of the change in the average markup. And the average markup is computed as the harmonic average of the microeconomic markup because this is what our theory wants. And it's a decomposition of this, the accumulated change in this markup into a within effect and a between effect. What you see is very striking in this economy, if you ignore the fluctuations and you focus on the trend, is that the within effect is basically equal to 0, and that it's all about the between effect. So the reasons markup are going up is because high markup firms are becoming bigger, not because individual firms are increasing their markups. And I believe that we were actually the first one to document this fact for markups. And this is going to have very profound implications for productivity. So this is an implementation of our decomposition. So this is the cumulated growth rates of aggregate TFP. So that's the distorted solar residual. In case you're curious, it's quite similar if you do the solar residual. The numbers change a little bit. And you have the decomposition into the pure changes in technology and the changes in allocative efficiency. And what's extremely striking is that about 50% of aggregate TFP growth over the past 20 years is due to reallocation effects, is due to changes in allocative efficiency. And you can understand why from what I told you about the composition effect about markups. The reason markups are going up is because high markup firms are getting bigger. High markup firms are getting more productive. We're reallocating resources to firms that had high markups and were too small to begin with. We're improving allocative efficiency. And it's not small potatoes. It's a very big effect. It's 50% of aggregate TFP growth. Now, this is what happens when you don't do the aggregation starting from the firm level. So we're taking the firm level markup, we're aggregating them at the industry level, and then we're performing the decomposition at the industry level. So we're ignoring the reallocation effects within industries. What you see is that there's basically no changes in allocative efficiency. It's all pure technology. So you would completely miss this effect if you started from the industry level. It is very important to disaggregate in this particular case to the firm level. So it really illustrates the importance of disaggregation. And you get very similar pictures, once again, for the other markup series. Now, I told you a lot about one way of thinking about changes in allocative efficiency. And what we're doing is we're comparing the change in the equilibrium output to the change in output that would have occurred if we hadn't changed the allocation. Okay? There's another thing that might be a reasonable thing to do, is you could compare the change in equilibrium output to the change in output that would occur at the efficient frontier. In other words, you could compute the change in the distance to the frontier. It's a perfectly legitimate exercise. It's a different one than the one that I have shown you. It's based on a different GE counterfactual. But importantly, it is also based on a GE counterfactual. It's a legitimate exercise that's not going to run into the kind of problems that I showed you before. So it's just a different notion of allocative efficiency. And we have theorems that help you think about these changes in distance to the frontier. So what we're going to do is a second-order approximation of the distance to the frontier for small wedges. And we're going to have two formulas. One formula that's going to be in terms of changes in endogenous objects. So you have to see the economy evolve through the shocks to implement it. And one formula that's going to be a structural formula in terms of economic primitives. So we can start with the first one. And you can see that it's a sum over all the different producers of the change in the quantity that producer J is producing because you're introducing the wedges, and the change in the wedge of producer J, divided by 2. So you recognize a Harburger triangle, and then you're summing these Harburger triangles with the sales shares of the different producers. So it's a formula that's reminiscent, actually, of a result of Harburger. But Harburger had a result for welfare, which required compensating transfer to neutralize distributive effects across agents. This is a result about output, about productivity, which does not require these implausible transfers. It's very important to understand that it's a GE decomposition. The changes in the quantity of output J are not just caused by the markup to producer J, by the wedge to producer J. It's caused by all the changes of all the wedges in the economy propagated in general equilibrium. Now, the structural formula expresses the changes in the quantities of the different goods in terms of microeconomic primitives. And you see that it's a sum over the producers of how big the producer is, how substitutable, how high is its elasticity of substitution, and how heterogeneously the producer is exposed to the different wedges directly and indirectly through the network. So you need a lot of variance of exposures for producer J, for substitution by producer J to matter. So you see the role of elasticities, you see the role of the input-output networks, and you see the role of the distribution of wedges on the input-output network. All these things are going to matter. More input-output intermediation is going to increase the distance to the frontier. Higher elasticities are going to increase the distance to the frontier. More dispersion of wedges are going to increase the distance to the frontier. So let me show you an implementation. So now I'm parameterizing the same model that I showed you before. And what that means is I have to pick elasticities. So I have to pick elasticities across industries and across firms within industries. The elasticities across industries are relatively low, as consistent with what people estimate. And the elasticities within industries are relatively high. We're taking 8, and I'll show you a robustness exercise. So these are computations of distance to the frontier for the 3 different markup approaches: user cost, accounting profits, and production function. You see that the distance to the frontier, the welfare gains that you would obtain by removing all the wedges, is gigantic. It's 20% for user cost, 17% for accounting profits, and 24% for production function markups, so the markups that Jan talked about. So these measures are 2 orders of magnitude larger than the estimates of Harberger, who computed something very similar. Okay? He estimated gain, misallocation from markups of 0.1%. We're finding 20%. The reason for that is we're disaggregating more. We're looking at the firm level, not at the industry level. There's a lot more dispersion at the firm level than the industry level. Second, elasticities of substitution are higher at the firm level than at the industry level. And third, we're appropriately taking into account input-output linkages, and he didn't do that. The other thing that you see is that this distance to the frontier increased between 1997 and 2015. So the allocative efficiency, according to this measure, decreased. This is surprising. I showed you another measure that told you that there were improvements of allocative efficiency. There was about 50% of aggregative P growth. What's going on? Well, once again, these are 2 completely different results with 2 completely different interpretations. One is about the contribution of reallocation effects to aggregate productivity along the equilibrium path. The other one is about changes in output in equilibrium compared to changes in output in the efficient frontier. So it's entirely possible that you have improvements of allocative efficiency along the equilibrium path and that the frontier is shifting even faster. And indeed, this is what's happening. This table is doing robustness by looking at how these numbers change when you change the environment. So in particular, if I reduce the elasticities within industries, so from 8 to 4, you see that I reduce the numbers quite a bit. I have the numbers, more or less. You see that if I trivialize the input-output network, I use a value-added economy, I divide the number by more or less 3. So input-output is very important when you want to think about misallocation. And this is what's happening when you're aggregating the markup at the firm level and you're just looking at misallocation across sectors. You see that the gains become absolutely trivial. So elasticities matter, the input-output structure matters, and it really illustrates the importance of disaggregation. So I have a little bit more time to tell you about nonlinearities. So not inefficient aggregation, nonlinear aggregation. So I'm going to go a little faster because I guess I don't have that much time. The first expression shows you the second-order derivative of aggregate output and its decomposition. So you see that the nonlinearities are going to be coming from the nonlinearities of aggregate output, even holding the allocation matrix constant. This function is nonlinear. And second, the reallocation effects are going to trigger some nonlinearities as well. But since we know that to the first order, the change in aggregate output is given by the Domar weights, then we know that the second derivative is given by the changes in the Domar weights. And then we have propagation equations, the very propagation equations I showed you, that are going to help you express the d lambda as a function of the structural primitives. So that leads you to a second-order approximation. Well, the change in output is the Holton term plus these nonlinearities that are captured by the product of the changes in shares and the changes in productivities. And then you can combine these with the propagation equations to know how d lambdas are changing as a function of structural primitives. So the changes in sales shares are ex-post-sufficient statistics. The input-output network and the elasticities are ex-ante sufficient statistics. And once again, the disaggregated details and the initial aggregation level are going to matter. So let me show you some examples. This is the horizontal economy that I showed you before. And I'm showing you the change in output as a function of the change in productivity of a particular producer. And I'm showing you different curves corresponding to different values for the elasticity of substitution. So the red line is Holton, and it corresponds to an elasticity of 1, the Cobb-Douglas case. You see that if you have substitutabilities, which would be relevant for if you're thinking about across firms within an industry, then the output function is going to be convex. So you're going to amplify positive shocks and mitigate negative shocks. Conversely, you see that if you're thinking about shocks across sectors, you probably want to think about complementarities. And then the output function is concave. That means that you're going to mitigate positive shock and amplify negative shocks. Okay? So Cobb-Douglas is really knife edge for nonlinearities, exactly as it was for distortions. And it has very profound implication for firm level versus sectoral level shocks. So here is an example to show you a bit the role of the network. It's a universal input example. So there's labor, that's the only factor. And labor can be used to produce electricity. And then you have a bunch of downstream producers that are producing from labor and electricity. And there's this number M that's telling you that a bunch of producers are going to be producing with labor and electricity. And then the other ones are just going to be producing with labor. And then you have two elasticities of substitution. A low elasticity of substitution, theta 1, it's the elasticity of substitution in production between labor and energy. And a high elasticity of substitution, theta 0, across sectors in consumption. So you see that basically if M is very low, then energy is not entering in a lot of places. It's not a universal input. That means that when there's a negative shock to energy, you can substitute at the macro level. So the sales share of energy is not going to increase that much, and output is not going to decrease that much. By contrast, if energy enters everywhere, it's a universal input, there's no way to substitute at the macro level. Okay? And so there's going to be a very pronounced increase in the sales share of energy following a negative shock, and a very sharp reduction in aggregate output. This is showing you the outcome of a model. It's like a sectoral model. And it's comparing two sectors, oil and retail, that turn out to have a similar sales shares. Okay? And what you see is that if you look at Holtons theorem, okay, for these two sectors, you get approximately the same thing. But if you look at the nonlinear effect, okay, if you take into account the nonlinearities, then a negative shock to oil is much more damaging than a negative shock to retail. So really the problem with oil is that it's this universal input. It's not just the elasticity of substitution of production, it's its position in the network that's shaping the macroeconomic elasticities of substitution of oil. Okay. And that helps rationalize the large asymmetric effects of oil shocks. This is an application that is showing you, is implementing the reduced form formula for nonlinearities and looking at the episodes of oil shocks in the 70s. So this is the sales share of oil. You see that it goes from something like 2% to something slightly below 8% at the end of the two oil shocks. So huge complementarities, really not a Cobb-Douglas world, a lot of nonlinearities. If you just look at a Holton sort of world, then you would multiply the shock to oil by a number like 1.8%, the initial sales share. Okay? And you would find that the aggregate effect on output of the oil shock is minus 0.2%. When you take into account the second order effects, okay, then you take into account the increase in the sales share. Okay? And so you multiply this number by a factor of 3. So it's very important to take into account nonlinearities to think about these shocks. This is an example that is showing you the importance of nonlinearities for a different phenomenon at a longer horizon. It's Baumol's cause disease. Baumol's cause disease is the idea that if you have complementarities across sectors, then sectors that are growing faster are going to see their sales shares decline over time. The resources are going to be reallocated away from them, and that's going to slow down the process of growth. So it is about nonlinearities. So if you ignore these nonlinearities, if you look at the first order effect, if you freeze the sales shares where they were in 1950, then you find the red line with no Baumol cause disease. And when you look at the full nonlinear effect or the second order effect, you incorporate the effects of Beaumont's disease. So by looking at the difference between these lines, you can quantify the importance of Beaumont's disease. And you see that's really quite important. It reduced aggregate TFP growth from 45 to now by about 20 percentage points. And it's really an illustration of these nonlinearities. And if you want to quantify these nonlinearities, you need to handle the disaggregation. You have no choice. Otherwise, you're going to get the quantities wrong. So there are a number of other applications that I didn't have time to describe. For example, we have a new paper which is about trade. And we're trying to really emphasize what are the disaggregated features that are important for thinking about trade models and questions that concern trade economists. So I'm just picking one of the conclusions that we have, which is about studying gains from trade. Okay? So you take a country and you ask, how much would this country lose if we went to autarky? Or how big are the gains from trade? So you have different columns here, and they correspond to different environments. And they're meant to demonstrate that it's very important to nail the elasticities, and it's very important to disaggregate. So the first column is basically where you have no input-output linkages. So it's the simplest Armington model. And you see the welfare gains from trade for a series of countries. For the US, for example, it would be 4.5%. So this is a number that's pretty typical. Okay? For those of you who know trade, this is like the basic ACR number. The second column is what happens when you allow for intermediate inputs, but you impose that all the elasticities of substitution across sectors are unitary. So it's Cobb-Douglas across industries. So there are no nonlinearities across industries. So what you find is that much bigger welfare gains, for the US, for example, they move from 4.5 to 9%. So it's very important to nail the sales share. And that's intuitive. No? If you're trading a lot, then the gains from trades are going to be larger. And then this column is showing you what happens when, instead of imposing Cobb-Douglas across industries, you try to feed in realistic elasticities of substitution across industries. So below 1, complementarities. And we're doing our best to pick elasticities that are consistent with what people estimate. And you see that these nonlinearities are about as important as allowing for intermediate inputs in the first place. So you really need to disaggregate. The disaggregated structure matters, the network matters, and the elasticities of substitution matter. So hopefully I've convinced you through all these different applications that it's really something that needs to be confronted, and that there's a value in developing these general and systematic methods to think about these problems. Thank you.
Well, thanks very much. I think we have a couple of minutes for a few questions from the audience. Yeah, I'm the closest.
Say that you are appointed as director of the Bureau of Economic Analysis. What would you do?
Agree on, which is that we need to make more disaggregated data available to researchers because it matters a lot, basically. So that's one obvious thing to do.
That the level of aggregation matters so much for our inference, for our measurement, I guess also may appear troubling to some. Specifically, what I have in mind is a multi-establishment firm where one establishment delivers to another, I guess would imply that the unit of reporting, of financial reporting, of accounting will matter for our inference. And taking this to the extreme, it seems you probably would like to have individual person-level information. Which obviously will be infeasible unless you become president of the BEA. So then I guess the question that I have is how do we think about this tension and what is the quote-unquote right unit of analysis?
So I think you can be a jihadist about it, and then you say, look, you know, we need to disaggregate, otherwise it's not kosher. I'm mixing jihadist and kosher, so I'm tired. And I don't think that's a very useful position. So I think you need to be pragmatic, basically. The problem is it's very difficult to know when disaggregation is going to matter quantitatively. In principle, it matters. But without doing it, it's hard to know if you're committing a small crime or if you're committing a big crime. But so David and I, we studied a bit the way people reacted to the Cambridge controversy. So it was a controversy around similar issues. It was about the aggregation of capital. Can you come up with one economic aggregate that you call capital and use that in your models? Or you know, are you committing a big crime by doing that? Because you're aggregating things that have nothing to do with each other. You know, buildings with like equipment and things of that sort. And so there was the Cambridge UK side that said you can't do that. And there was the Cambridge US side that said, no, actually you can't do it. It came after Solo's growth model, and that was a model with an aggregate production function and using capital. And after some back and forth, Cambridge US conceded to Cambridge UK and said, yes, you're right. You know, if we do this, we're committing a crime and we can run into problems. And people reacted very differently to this. So Solo was forever the pragmatist. You know, he was like, there are two ways to react. You can go highbrow, which means like you insist on disaggregation, writing disaggregated models, or you can go lowbrow, which means to say, don't bother me about all of this. I'm just going to do, you know, what I'm used to do and get numbers and everything. And he said, I'm middlebrow. And I think it's a good position, actually. And there's another quote that maybe I want to give you is by Samuelson, who said, like, yes, too bad, we need to disaggregate for the thing to be really solid and consistent. And then he has a line that I'm not going to be able to reproduce exactly, but he says, you know, if some people are nostalgic of the time where you didn't have to worry about these things, that they should be reminded that scholars were not meant to have an easy life. So I guess we need to deal with it, but pragmatically, hopefully.
Okay, well, I think we're out of time, so I'm going to end it here. So thank you, Emmanuel, for your talk.